Yes.
Yeah.
Uh, Good afternoon to one and all present here. Now I welcome our keynote speaker, Dr. Nagesh Kumar sir, with a brief introduction. Actually, he is currently working as a director in the Center for Energy, Environment and Productivity, Chennai. Sir has total 27 years of experience with NPC in the field of energy management. And Sir has handled numerous projects related to energy management and he has attended various national and international level training programs and he has presented many research papers in various conferences and also he authored three textbooks and his professional certifications include accredited and certified energy auditor by Bureau of Energy Efficiency, Ministry of Power, Government of India, and also is a qualified lead auditor in ISO 14001 and qualified lead auditor in ISO 50001. We are very happy to have you here, sir. So now I request you to deliver a technical talk on steam utilization, energy conservation techniques, sir. Over to you, sir.
Yeah. Thank you, Dr. Sham, and
Thank
good afternoon to all the participants. So it's a pleasure for me to talk from the podium of Anna University. So in today's session, we will discuss about the steam system. I think already you must have seen about the boilers, how steam is generated. So once the steam is generated, how efficiently we are distributing and utilizing the steam is what is going to be the topic for this session. So as you would have seen, the boilers are now fairly efficient. So before the oil crisis in 1970, before 1973, the boiler efficiencies were hardly 55%, 60% with uh, huge exhaust gas losses, high exhaust temperatures. But today, over the years, we have seen an improvement in boiler efficiencies and it has reached almost 83 to 85%. So you will find that there is not much of a scope for improvement in boiler efficiency. Already all the standard measures like condensate recovery and providing economizers, air preheaters, bringing down the exhaust temperatures. So all these measures, if already taken, then it leaves very little room for further efficiency improvement. So basically, when I say efficiency improvement, our objective is to reduce the fuel consumption for the same output. So if you consider the entire boiler plus steam, you will find boiler is almost saturated in efficiency, about 85%. So this 85%, that means whatever the heat in the fuel, the chemical energy in the fuel has been converted to heat energy. The heat energy has been transferred to the water in the form of steam. So 85% of the kilocalories in fuel has been transferred to steam. Now the steam is going around from the boiler. It leaves the boiler house with carrying 85% of the heat content of the fuel. Now in this 85%, how we can save steam, heat losses, heat requirement optimization, all this, you will find there is a tremendous scope. So all the improvements oriented towards fuel conservation, fuel reduction will start from the efficient use of steam. That is where the major scope lies. But before going into the utilization, let us see why steam is used as a heat transfer medium. So we can directly have a flame or a combustion system for every heat exchanger. Basically, what we are doing in a boiler, we are generating steam, taking the steam to different parts of the industry and using it for heat transfer purposes in the heat exchanger. Why do we do that? Why do we use steam? Why can't we have small little combustion systems for every heat exchanger? See, one thing is steam as a heat carrier has one of the highest specific heat. As you know, the specific heat of water is 1 kilocalorie per kilogram degree centigrade. Whereas for other material, if you say steel, it is only 0.12. The specific heat of steel is 0.12 kilocalories per kilogram centigrade. And if you take air, specific heat of air is only 0.24 kilocalories per kilogram degree centigrade. So water, on the other hand, has 1 kilocalorie per kilogram degree, almost 4 times that of air, the specific heat, which means it can carry large amounts of heat in a given mass. And another important thing is the latent heat. So the latent heat property of the steam is one which is most important when we talk about transferring the heat. So we will see what is this latent heat. And it has got one of the highest heat transfer coefficient. So easily it can transfer the heat from steam to the other medium in the across the heat exchanger. And also it is easy to control and distribute. So you have a valve, steam valve. If you want steam, you open it. If you don't want steam, you close it. So easy to distribute in a pipeline. And another important thing is water is cheap. It's available everywhere. And also it is inert. So when there is a leak of steam, it is not hazardous like many other substances. So it's an inert substance. So no damage done to the environment and the people around in terms of its chemical properties. So steam just mixes with the air. So for all these reasons, steam is used as a heat transfer medium. Now we were talking about this concept of latent heat. So what is this latent heat? Why it is important? Now, if you look at this property diagram, say let us say we start this point, water, we are going to boil water. Water is at, let's say, 30 degrees. And 30 degrees we keep on boiling. It reaches B, a point B where the temperature keeps on rising and it reaches 100 degrees. So now the temperature is 100 degrees, 100 degree water. If we continue to add heat, then what happens? There is a phase change that is happening. The water is converted to steam. And by the time it reaches C, it is almost 100% steam. So temperature does not vary. Temperature remains 100. So this portion where we have added heat for converting 100 degree water to 100 degree steam is called the latent heat. So this particular from here to here. Okay, this is called the this latent heat component. This is the latent heat. So, and the heat that was added from 30 degrees to 100 degrees, how much heat was added? That is called the sensible heat. So this is sensible heat and this is the latent heat part. So as you can see, latent heat is almost 4 times the sensible heat, nearly 4 times the sensible heat. So what is the significance of latent heat? Let's say we are using a pressure cooker for cooking. So in a pressure cooker, we are going to say make rice. So the pressure cooker has got a vessel here. And now we start the stove. Inside we are keeping rice and water. Now the flame is on. After some time, what happens? Whistles are coming. Okay, 1 whistle, 2 whistle, 3 whistles. So maybe after a few whistles, we stop the stove. When we stop the stove, what will be the condition inside the cooker, whether the rice would have been cooked or not. So what do we do when we are very hungry? We try to slowly lift this weight ball with a spoon and we want to release the pressure because it is pressurized, we cannot open. So we use a spoon and release the pressure. And then you open, you find that rice is not cooked. So even after 4 or 5 whistles, immediately after that, if you open, the rice is not cooked. So when does the rice cook? Now, when the whistles are coming, the pressure cooker has only acted like a steam generator. It's a boiler. It's generated the steam. After we switch off the stove, the steam inside the pressure cooker starts transferring the latent heat to the rice. In the process, steam condenses. So when steam condenses, it gives up this much amount of latent heat. So the latent heat is given to the rice and then the rice cooks. So uh, this is the concept of latent heat. So in a latent heat situation, so this is at let us say 1 bar pressure. At 1 bar pressure, this is the latent heat. Now at 2 bar pressure, this is the latent heat. At 20 bar, maybe further higher. So 20 bar, this is the latent heat. And 60 bar, 80 bar, 100 bar, like that keeps on going. So what you observe is as you increase the pressure, the latent heat is decreasing. Okay. So the latent heat decreases as you increase the pressure, which means that we should use the lowest possible or practical pressure for any of our heating applications. So when you use lower pressure steam, latent heat is more and more heat is transferred from the steam to the substance, which needs to be heated. Now, as you keep increasing the pressure at one point, the latent heat becomes zero. From the shape of the curve, you see, you keep on increasing the pressure. So it reaches 200 bar and at 221 bar, 221.2 to be exact. At 221.2 bar, the steam reaches a state called critical point where the latent heat is zero. So as you can see here at this point, the latent heat is zero. This occurs at 221.2 bar and the corresponding saturation temperature is 374.15 degrees centigrade. So for each pressure of a boiler, there is a corresponding saturation temperature. For atmospheric pressure, it is 100 degrees centigrade. And for 221.2 bar, it is 374.15 degrees centigrade. See, this latent heat is required basically for heating purpose. When you want to heat something, the steam will condense, it gives up this latent heat and heat the substance. But in the case of power plants, we don't need any heating. We want kinetic energy, steam energy in the steam, enthalpy of the steam has to convert to kinetic energy to rotate the turbine. So there's no heating involved in the case of steam power plants. So that is why you will find that nowadays the boilers in the power plants, the modern power plants operate at supercritical cycles. That means the pressure involved in the power plants is beyond 221 bar. It may go up to 240 bar also. So there's no latent heat. Directly it goes beyond the critical point and goes into the turbine, generates kinetic energy for power generation. But in the case of industrial process applications where heating is required, you have to go in for what is known as saturated steam. Subcritical and saturated. Saturated means it stops at this point. As you can see, it reached 100 degrees, it stopped, 100 degrees steam. But if you heat it further, this 100 degrees steam, if you heat it further, then the temperature increases. So water has converted from 100-degree water to 100-degree steam. Further heating, there is a superheating involved. The temperature rises now. Here the temperature is constant during the phase change. Or temperature rises. So this is called the superheated region. So in the superheat region, the temperatures are higher than the saturation temperatures. So superheated steam is used in the power plants. Why superheated steam is used in a power plant? So the higher the temperature, the higher will be the efficiency. So if you say Carnot efficiency, it's T1 minus T2 by T1. T1 minus T2 by T1. So that means if you want to maximize the efficiency, you have to maximize T1. So the higher the T1, the more the efficiency. And that is achieved by superheating the steam in the power plant. Then similarly, the lower the rejection temperature, T2, lower temperature, as low as it is possible, if you have, the efficiency is going to be the highest. So T2 is reduced by keeping the condenser in vacuum. So take it to a very low pressure where the corresponding temperature will be 45 or 55 degrees centigrade. To that vacuum you are maintaining the turbine outlet. So the efficiency of the Rankine cycle is maintained at maximum. So these are all some of the properties of steam. So if you see a typical boiler, if you're talking about small boilers in processing plants, processing industries, the steam coming out of the boiler may not be fully saturated. There will be some amount of moisture carryover in the steam. And for example, for a boiler which is operating at a pressure of 8 kg per, this is a small boiler we're talking about. Steam saturation temperature is 170 degrees centigrade. And the steam enthalpy is given by HF, that is sensible heat plus latent heat. So corresponding to this pressure 8 bar, sensible heat is this much, latent heat is this much, the total heat is this much. So this is for a pure saturated steam. That means all the water has been converted to steam. But there will be some amount of moisture. Let's say the same steam contains 4% moisture. Then the effective enthalpy. Enthalpy is the heat content. So this is what is known as the total enthalpy. What is the amount of heat carried by steam per kg? 660.81 kilocalories. And if it contains 4% moisture, the total heat is given by sensible heat. It has been raised to 100 degrees anyway. So entire sensible heat is transferred. But only 96% of the water has been converted to steam. That means the latent heat is only 0.96 into 489. So effective enthalpy, you can see it is reducing. There's a reduction in the effective enthalpy of steam. Okay. So wet steam means lower enthalpy. That means we may have to use more steam for the same requirement in the process. These are typical steam tables. So you'll find the pressure is 1, and for 1 bar pressure, the temperature is 100 degrees centigrade, and you have the sensible heat. The sensible heat is almost equal to the temperature. Whatever temperature, because the specific heat is 1, so sensible heat is nearly equal to temperature, as you can see. Latent heat, if you see, as the pressure increases, keep on increasing the pressure, the latent heat will keep on decreasing. So as you can see, 539, 526, it keeps on decreasing. The total enthalpy, however, will increase because latent heat is increasing. So for us, if we are going to use a boiler in a process industry for heating applications, the latent heat is of concern. We need to worry about the latent heat and see that the pressure, what is the pressure, minimum pressure you can operate. If you can operate at 2 bar, then you'll get 526 latent heat. If you get maybe 6 bar, there will be 498. But it depends also on the temperature what you want. You may also operate 1 bar. You may get the highest latent heat. But the temperature is maximum what you'll get is only 100 degrees. Suppose you want to heat some fluid to 120 degrees, then probably 1 bar will not work, though it has got high latent heat. So you may have to go in for 4 bar, where steam temperature is 143, which on the other side after heat transfer it will be 120 degrees on the user side. And this is specific volume of steam also reduces as the pressure increases, specific volume, meter cube per kg will reduce. Now, a typical steam distribution system consists of this. So, this is right from the boiler, steam is generated. It goes like this. Steam goes, and this is, let us say, a closed vessel in which some steam jackets are there. So, outside, jackets are provided through which steam will go. So steam goes inside the jackets, gives up the steam to the container. Inside something is to be boiled or heated. So what happens is steam condenses. Steam condenses and the condensate comes out like this. So when the steam condenses, a large amount of heat is transferred. So inside the pan, whatever substance you have kept, it boils. What happens to the condensate? So when the steam condenses, you have to remove it so that successively some steam will be coming and heating. Now, how to take out this condensate without taking out the steam? So steam continuously coming turns into condensate. Condensate only should go out. Suppose you have a valve here. Imagine a valve and you are slightly keeping it open. So condensate comes, steam comes, it condenses into condensate. The condensate comes out, but steam also will come. So we need a special type of valve which will allow only the condensate to come out, but not the steam. Steam should condense inside, give up the heat. It should not come through the trap. This is this valve, this special valve which allows only the water or liquid to pass and not the steam is called a steam trap. So a steam trap is a device which allows only the condensate to pass. Condensate is after steam condenses, whatever water you have is the condensate. And so this is a steam trap, a special type of valve which allows condensate to flow but not the steam. So steam goes to several equipment in the process, and finally the condensate, whatever you have here, they are all returned back to the boiler. So condensate is nothing but distilled water. You are generating steam and then condensing it. So it's basically distilled water. So purest form of water. So maximum whatever condensate has to be recovered and sent back to the boiler because your feed water treatment cost will reduce. The second thing is the condensate itself will be at a slightly higher temperature, 80 to 90 degrees centigrade will be the temperature. And when you send back the condensate in hot condition to the boiler, you're going to save fuel in the boiler. For every 6-degree rise in the boiler feed water temperature, there will be a 1% saving in fuel. So this is a typical steam system, distribution system in an industry. And what should be the pressure of steam? The working pressure of steam, initially how you decide the working pressure of steam. So mostly by the maximum safe working pressure of the boiler. Whatever boiler you want, you have selected based on the maximum temperature required in a process. The temperature depends on the pressure. So we see what is the maximum temperature required in the process. Accordingly, we select a boiler working on that pressure. And what is the minimum pressure required at the plant? So what is the safe working pressure minimum between these two? The boiler can operate. And there is also a pressure drop that happens because steam passes through a long pipelines. There's a pressure drop due to friction. And also, steam, when it condenses, it loses specific volume. So there also it will lose pressure. Pressure is reduction is due to, or pressure loss is due to the frictional resistance and also the condensation within the pipework as the heat is transferred to the environment. Now, these are the factors to be considered, the general layout of the steam. So, where the boiler system is and where the heat utilizing equipment are, steam utilizing equipment are, what should be the pipe sizing, and whether any pressure reducing or desuperating stations are required, air venting, steam pipe insulation. These are all some of the aspects that we need to look into. So, firstly, when we see the features of steam piping, like any other fluid, steam also depends on the steam pressure or pressure loss depends on the velocities. Okay, so we need to see the velocities within the limit, and also when the steam is moving around, you can there should be facility for proper draining of the condensate. So what does this mean? So facility for draining of the condensate means the steam is flowing here. So because of radiation convection loss to the environment, some steam will condense. In spite of the insulation, some condensation takes place. So whenever there is a condensation, it has to be removed. If you don't remove, what will happen? So if you don't remove this, suppose this is called the drain pocket. So as the steam moves, in this drain pocket, the condensate alone is collected and it is taken out through a strap. If you don't have this, then steam generally travels at 30 meters per second, velocity of steam. Liquids like water, generally the velocity is about 2 meters per second. Steam at 30 meters per second, water at 2 meters per second, there's a tendency for the steam to drag this water also at 30 meters per second. So when water goes at 30 meters per second velocity, it's got a huge power density. So it goes and bangs against a wall or any bend or restriction. It can be ripped apart. The entire pipeline can be ripped apart because of a phenomenon called water hammer. So the water hammer occurs when steam carries this water at its velocity of 30 meters per second. And so steam pipe should be laid by the shortest possible distance rather than to follow a building. Now, shortest possible distance means the pressure drop can be maintained less, and also the radiation and convection losses will be less. This is the proper draining of condensate, what we have seen. And a 100 millimeter well insulated pipe, 30 meter length, carrying steam at 7 bar, will condense nearly 10 kg of water in the pipe in 1 hour. So there is a slope that is given. So in this case, the pipeline will be sloped like this so that easily the water can be picked up through this drain. And every 30 to 50 meters in the pipeline, you should have these drain pockets. So the Condensate is discharged. Yet another thing that you see is the expansion loops. So in the steam system, you will also find that there's something called an expansion loop. So you have a steam piping like this, then you will find some of the industries they have a system like the steam is looped like steam piping is looped like this. So why? Because when you start the plant, the steam is in cold condition. So there's sudden heating of the pipeline. If you don't have this, the pipe when it is rigid, it tends to expand and there will be a crack. So this kind of expansion loops helps to accommodate for the any expansion due to differential temperatures. And this is the velocities we are discussing. So 50 to 70 meters per second for the superheated steam, and saturated steam will be slightly at a higher velocity, lower velocity, 30 to 40 meters per second, and wet steam will be at 20 to 30 meters per second. So superheated steam is hardly having any moisture or water droplets. Saturated steam not supposed to have any droplet, maybe a little bit of droplets will be there. Wet steam will have a lot of water droplets. So when you subject it to higher velocity, there will be an erosion. So normally the wet steam is kept at 20 to 30 meters per second and saturated. So the average velocity of saturated steam, we can take it as 30 meters per second. And it's similar to any liquid. The steam flowing from one part to another part, there is going to be a pressure drop, and the pressure drop again depends on this Darcy's friction factor, 4FL V squared by 2 GD, where F is the friction factor and length of the pipe, velocity squared, and inversely proportional diameter. So from this you can see that the velocity or the frictional loss is inversely proportional to the diameter. Not only that, since it is velocity squared, so what is velocity squared? What is velocity? This will be Q by A, right? So velocity will be so if you see this U, this flow divided by area. You can also write Q like this, flow divided by area squared. Okay. Now this U is Q squared by A squared. So A squared comes to the bottom. So you have an A squared here. A squared is nothing but pi D squared by 4. So D squared is there inside this A. D squared will give you D power 4. So actually if you see this HF, the friction factor is inversely proportional to the fifth power of the diameter power 5. So what does it mean? Even a small change in diameter can have a significant impact on the frictional loss. So when we are designing the steam system, we have to ensure that the diameter is adequately sized so that the pressure drop is minimized. So this is an example. Determine the difference in pressure between 2 points 1 kilometer apart in a 150 bore horizontal pipework system. So in this case, the water is selected, but same thing applicable for steam also. So where we take water flow rate as 45 meter cube per hour and the friction factor is 0.005. So from this, we know the flow, 45 meter cube per hour. We know the cross section area, the diameter, you can see the area. So Q by A gives you the velocity. The velocity is coming to 0.71 meters per second. So we put this in this equation, 4FL V squared by 2 GD Over friction factor is 0.005, 1 kilometer apart, 2000 meters into this velocity squared by 2 into g into diameter 150. So you get 3.43 meters or 0.34 bar as the pressure drop. So this is a simple calculation for assessing the pressure drop in pipes. Now pipe sizing, you can go in for a big pipe. A balance is drawn between pipe size and the pressure loss. Higher the pipe size, lower will be the pressure drop. So what is the significance of lower pressure drop? Suppose your boiler is generating at 7 bar and in the farthest end you are getting only 6 bar. But that particular user, he wants 7 bar, which means you have to raise the pressure of the boiler from 7 to 8. So you keep 8 bar in the boiler, then the final user will get 7 bar, what he wants. Now this pressure drop, could it be 1 bar or 0.5 bar, depends on the pipe size. So the pipe size determines the pressure loss. And of course, it should be within the available velocity, permissible velocity. And as we said, the pressure drop change will be inversely proportional to the fifth power of the diameter change. And the pipe size calculations are again fairly straightforward. You know what is the permissible velocity. So I say velocity not to exceed 25 meters, but you design for this. We want to keep 25 meters per second as the velocity in the pipe. So once you know the velocity, once you know the flow, you can find out what is the area, and from the area you can find out what is the diameter. That's what has been done here. A straightforward calculation. Okay. Now, in some cases, there's a boiler, and let's say the boiler generates steam. Okay. Now, this is generating, let us say, at 20 bar. The boiler is generating steam at 20 bar. See, one particular process requires 17 bar. Then the other users, they need only 3 bar. So what to do? Here we have to put some pressure reducing walls which will reduce the pressure. Okay, it will be like this. Pressure reducing walls. Now, if you send in 20 bar here, the outlet you will get 3 bar. Okay. So why de-superheating is required? So as you have seen earlier, you have a figure like this. So steam goes, gets heated up, latent heat is transferred. At this pressure, this is a 20 bar. Let us say we reduce it to 3 bar. So 3 bar will be a constant enthalpy process. Enthalpy remains the same. As you reduce the pressure, you see it has gone into the superheated zone. Right of this bell-shaped curve, we had said that it's superheated zone. So when you reduce the pressure, it becomes superheated at that particular pressure. But superheated steam is not good for the process. Superheated steam is a very poor conductor of heat. Almost like behaves like a perfect gas, very poor heat transfer coefficient. And also the temperature has to slowly come down from a superheat to saturated, and then only heat transfer will occur. So we don't want the superheated steam for the process heating. We may need superheating for power generation, but not for process heating. So what we do is we spray some water here in this outlet. The superheated steam, after getting some water into it, it becomes saturated again. So that's why this whole thing is called the pressure reducing desuperheating station. It also gets desuperated, bringing back to the saturation stage. Air venting. This is another important concept in steam. Like when you make rice in the rice cooker, you would have seen there is some air trapped inside the cooker. As you close the lid, inside the cooker there is some air above the water what you have kept. This air as we know is a very poor conductor of heat. It obstructs the heat transfer. It acts as a barrier to heat transfer. So this air has to be removed. So what we do is we don't put the pressure cooker or the whistle, the weight valve immediately after starting the stove. You wait for some time, allow the air to go out, then you put the weight valve. You will find the cooking time will be faster because the air is vented out and you have perfect heat transfer. So cooking time reduces. Similarly, in the industrial system, suppose when we stop the plant, what will happen? The pipeline is full of air. So when you start the plant, this first steam that is coming from the boiler, it pushes the air into the system. It pushes the air in the system to the equipment. From the equipment, it goes to the trap. Trap does not know how to vent air. So we need an air venting system. At the farthest end of the steam main pipeline, we have this kind of a vent. So the steam that comes out on a Monday morning when you start, all the steam pushes the air. It comes here and it goes through a vent here. It's open in cold. So all the air goes, then the steam comes. It's a thermostatic vent. It gets heated up and then it closes. So all the air is vented out. This is the typical air venting in a steam system. And if there is a mixture of steam and air, you can see the impact. So 20% air is entering in the system at 5 kg per centimeter squared. So 80% steam, 20% air. So this is the effective pressure you can see, 0.8 into 5 at 5 bar and zero point 0.2 of air at 5 bar. Air also will be at 5 bar. So you get 4 kg plus 1 kg is the, if you go by the partial pressures of the total 5 kg, steam is contributing to only 4 kg and air is contributing to 1 kg. Now, the temperature of the steam at 5 bar will not be saturation temperature at 5 bar, but it is a temperature corresponding to 4 kg. Okay. Now, if the pure steam, if all the pipeline consisted only of steam at 5 bar, the temperature is going to be 158. Whereas, if it is a mixture of air and steam, the temperature at 5 bar will be only 152. So, presence of air will bring down the temperature and it may affect the quality of the products that you are producing. You may be thinking that we are setting steam at 5 bar, but effectively the steam temperature will be less. Now, one of the fundamental things in steam savings is to insulate, because steam is a hot carrier. The pipelines will be hot. So if you want to save steam, the first step, simple thing is to provide insulation for the pipelines. So when you provide insulation, we conserve energy by preventing the heat loss. So all the heat losses in the system is prevented, and facilitate temperature control of a process. Suppose the boiler you start at 173 degrees centigrade. As you keep on going in the pipeline, gradually temperature becomes less, it becomes 160 by the time it enters the process. Then your process is going to suffer. It is not getting the required temperature. So to avoid that loss, you have insulation, then the difference between the boiler and the end user will be very marginal. And also to prevent condensation of steam. Steam should not condense the pipeline, as we have seen. So to avoid that, we have to avoid heat loss. So we need to provide insulation. Then prevent or reduce damage to pipe from exposure to fire or so this also insulation also plays a role in protecting the pipe or the assets from the fire and also the corrosive atmospheres. It doesn't allow the atmospheric moisture to enter and corrode the pipelines. And also control surface temperature for personal protection. One more thing is wherever you touch any part of the equipment in a plant, it should be safe. It should be less than ambient plus 30, ambient plus 10. So if the ambient is 30 degrees, any part of the surface in the plant should not be more than 40-45 degrees for to be safe. So to ensure the safe conditions, we again are insulating the pipelines. So here you can see the impact of insulation. There is a half an inch line. Then the thickness 15 inches, 15 mm we have provided. If it is insulated, the radiation loss is only 125 kilowatt per meter. If you don't insulate, it's almost 6 times 692 kilowatt per meter. So as you can see, there's a dramatic effect on insulation. As increasing pipe sizes, uninsulated, insulated versus uninsulated. You'll see the difference. Even the flanges, see many times there's a tendency to leave aside the flanges. The flanges, the bends, everything has to be insulated. The flanges also cost a lot. So a lot of heat is escaping from the flanges. So all the flanges, walls, wall bodies have to be insulated. Now coming to this efficient steam utilization, what is the efficiency of the steam system? Now as you have seen fuel, in the fuel there is 100% heat in the form of chemical energy. It goes into the boiler, combustion takes place. Out of this 100%, 80% is going along with the water, steam. 20% the loss in the boiler, flue gas, dry flue gas loss, wet flue gas loss, radiation loss, all that constitute 20%. So remaining 80% is the efficiency. So this 80% steam, 80% heat and steam is going to the distribution. That means it is carrying through the pipelines and little bit of loss, 5% loss is there due to insulation. Even though if you provide insulation, there may be 5% loss. It reaches the process. So 75% of the fuel's heat has reached the process. In the process, let us say there is a heat exchanger. You want to heat something. So, or dryer. Let us say we take in this case, there is a dryer. A steam dryer is there. So we are giving 75% of heat. And after drying, the raw material, the whatever has been the input for this process, it comes out at a higher temperature. So it carries some heat with it, which is about 35%. So 75% is the heat input, 35% heat carried by the product, 25% is escaping as losses, heat losses. And the condensate, so steam goes, condenses, gives a condensate. The condensate carries about 15% of the heat. So the condensate return system going back to the boiler. So if you see the generation efficiency, output by input, 80 by 100, 80%. Then distribution efficiency, 80% goes, 70% comes. So 75 by 80, that will be 83%. And the utilization, 75 goes in, 35 comes out. So 35 by 75 gives you only 47%. steam utilization efficiency is only 47%. So that means this is the place where majority of the energy saving potential lies. So we can see some case studies later how this 47% can be further enhanced. Right. Okay. So yeah, this is a simple how to estimate, how to assess the performance of a steam system. For example, a milk evaporator uses steam jacketed kettle in which milk is processed at atmospheric pressure. The kettle has a 680 kg per batch capacity. One huge kettle is there, 680 kg per batch. Milk is heated from a temperature 26 to 100 degrees, where 25% of its mass is then driven off as vapor. We are trying to condense the milk. Determine the amount of 1 kg per centimeter squared steam required per batch, not including the heating of the kettle itself. So only the contents we are concerned, and specifically the milk 0.9, latent heat of steam is given. So this is the quantity of water evaporated from the milk. 25% of its mass is driven off. That means 680 kg is the batch. 25% of it goes off into the atmosphere, boiling off. That is 170 kg per batch. So heat required to raise the temperature 26 to 100 M Cp delta T, 680 into 0.9 into 100 minus 26. So this so many kilocalories per batch is a sensible heat required to raise the milk temperature from 26 to 100. Then 170 kgs is driven off, so it boils off, becomes vapor and goes in the atmosphere. So how much heat is required? 170 into 540. 540 is the latent heat of steam at that pressure and ambient pressure. So this will be about 91,800 kilocalories per batch. Total heat required is for sensible heat and for the latent heat. So this much is the heat required. And what is the quantity of steam required? Quantity of steam divided by the enthalpy of steam. Okay, so this will give you the actual steam consumption per batch. How much steam is required? 261 kgs of steam will be required. So this is how the steam consumption is calculated theoretically. But practically, in a heat exchanger, how to actually measure the steam consumption? There's a heat exchanger. Okay, the steam comes here, condenses, and leaves a trap. So in this trap outlet, only condensate is coming. So we can open the flange at the outlet of the trap and collect the condensate. If it's a low pressure steam, collect the condensate in the bucket and see how much condensate is collected over a period of time. And that gives you the kg of condensate collected per unit time, per hour or something. So how it will indicate the steam consumption? It is that law of conservation of mass. Whatever steam enters here, mass of steam entering the heat exchanger is equal to mass of steam leaving the heat exchanger. So this entering mass, exiting mass, same in terms of mass. So whatever the mass of condensate flowing here is nothing but the mass of steam that was sent here. So this is in practice we actually do this kind of a collection. Open out the trap, put a hose, bring it to a collection tank, and then we actually measure the amount of steam consumed in the equipment. Now, in some cases, see, there is a heat exchanger. Okay. Steam is sent at say about 7 bar. 7 bar steam is sent inside, and what comes out here will be 7 bar condensate. So 7 bar steam here, 7 bar condensate here. Now, as the condensate comes out at 7 bar, the water temperature will be around 160, 165 like that. So water at 165 cannot remain like that. So some portion of the water will flash into steam. So what we are doing is we are taking that low pressure steam and putting it into this device called, here it is, the thermocompressor. So this low pressure steam at say 2 bar. So now you can also flash the steam to the various pressure that you want. Okay. So this is a 7 bar steam here, 7 bar condensate. You can flash it to 2 bar or even atmospheric pressure. It goes. So entry is here. Now there is one more 7 bar steam you have here. You use this as what is known as the motive steam. So 7 bar here. Let's say 1 bar flash steam here. So 1 bar will get converted to say 3 bar or 4 bar, whatever you want. So the outlet, when it comes, you will get at this place 3 bar. So higher pressure steam. The thermocompressor is a device which converts low pressure steam to medium pressure steam using high pressure steam. So wherever medium pressure steam is required, we can upgrade the low pressure steam to a medium pressure steam using high pressure steam. This is a typical dryer. So in a dryer, very common in many of the industries, steam is used for the drying. We have some products. Let's say textile fabric. The textile fabric, after dyeing, it is going into a dryer like this. So the moisture has to be removed. So we use steam. Steam will go through the tubes, and then in that radiator type of heat exchanger, we blow the air over the steam coils. Hot air will go and remove the moisture from the cloth fabric. So this is a typical dryer. Okay, so a hot air dryer using steam. There are different applications of steam. And as we have seen, there are these devices called steam traps in the system. What is the function of a steam trap? So one, to discharge the condensate as soon as it is formed. Discharge condensate as soon as it is formed. Because continuously steam should come inside so that heating will take place. So as soon as condensate is formed, that means the heat has been given up by the steam to the product. So this condensate has to be removed. Should not allow steam to escape. So when you open through the trap, only the condensate should go. Steam should not go. To be capable of discharging air and other incondensable gases. So in addition to steam, as we said initially, there could be some non-condensable. That means air and other gases which will not condense. So this will go and create blocks in the system. So they have to be discharged. So it also has to function like an air discharging device. So how that steam trap works? There are many different types. One type is what is known as a thermostatic. Oh, this is a float and thermostatic. The float type of trap. So what we do is we have a heat exchanger. The heat exchanger is here. and steam is coming here. Condensate comes and goes here. So condensate outlet of the heat exchanger is connected to this flange of the trap. Condensate goes inside like this and falls. This blue one is the condensate. And outlet, you have a needle valve like this with an opening here. Now, as the level rises, the float also lifts. The float lifts and then the condensate flows out like this. When steam comes, the float does not lift because of the density difference. So the float remains in that position and steam is trapped. It does not allow the steam to go, but it allows only the condensate to go. The typical float trap. And there are different versions here. We have float and thermostatic, where initially, the air and other things will have to be flushed out. Suppose air enters the trap, then this air will not condense, so it will block the operation of the trap. So initially, the thermostatic valve is there, which will allow the initial steam to go through the bypass. This is a bypass line. So it will flush out all the air, and after that, when the heating takes place to the thermostat, the pipe is connected like this. So henceforth, all the steam will be going through the trap. And this is a thermostatic. Thermostatic means there is a expansion container bellows type. Inside there is some sealed. It's a sealed bellow. Inside some expanding liquids are there. So when steam comes, the bellows expand and blocks this path. When condensate comes, it does not expand, so easily condensate can go out like this. Similarly, here you can see a thermostatic type with a bimetallic strip here. The bimetallic strip is actually going to expand when steam comes. When it expands, it takes a bow shape like this, and you can see this is closed, completely closed. Okay, so this is a thermostatic trap. And we have seen this ball and float trap, and this is an inverted bucket trap. Inverted bucket trap has a body of the trap will be like this. So you find that the heat exchanger outlet is connected like this. So the condensate comes here, it enters this what is known as an inverted bucket inside the trap. Inverted bucket inside the trap, the condensate comes, then it flows out, it goes like this, and then it out. When steam comes, what happens? The outside body is full of trap. Inside the bucket, it is steam. So there's a density difference. So the bucket rises. The bucket rises, and here the valve is closed completely. After some time, the steam condenses, and then depending again condensate or steam, this movement will be up and down. This is an inverted bucket trap. So different types of traps are used depending on the situations. Like this is a thermodynamic trap. Thermodynamic, as the name implies, it uses both the thermal and dynamic properties of steam. See, what happens is here you have a, okay, the inlet will be like this, the strainer, and then here you have a lid. So the top view, if you see, it will be something like this. Okay, then there will be three holes like this. One, two, three. Okay, holes. Now, this is the disc. Okay, this disc is sitting like this. The condensate comes, so it is sitting on freely floating, sitting on these outlets. Condensate comes through the strainer, it lifts the lid by its shear force, and then all the condensate comes out like this. Okay. Now, if steam comes, what happens? So steam is coming through the strainer, it goes. Then the steam travels at a terrific velocity under the disk. There's a huge velocity, and as we know from Bernoulli's principle, when the velocity increases, the pressure will decrease. So, because of high pressure, high velocity here, the pressure will decrease and the lid will come and close completely the trap. The lid will be shutting the trap. So, no more steam can escape. So, this is a typical. Then, after some time, the steam will condense, and again, the same operation, whether steam or condensate, same operation will take place. Okay. Then, the traps, as we said, depends on the nature of application. So there are different types of traps for different applications. Thermodynamic traps, for example, are mostly used for the main lines, main steam lines. So this thermodynamic, the steam traps itself can be, you can have sometimes a group trapping for a set of equipment connected to a common condensate line. You can have a common trap, group trap. Or you can have an individual trapping. This is again, you have to make a choice in the beginning whether it should be group trapping or individual trapping. Group trapping means, suppose here the condensation is faster, more condensate is coming out like this, it will block the flow of condensate from this. So it may affect the heat transfer here. So where there is a consistent heat transfer, so here also there is sufficient amount of condensate generated, here also similar amount of condensate, then this kind of system will work. So you can save on the initial installation cost, monitoring and all that. But where there is a differential heat transfer rate, then best thing is to go in for an individual trap. This is the water hammer, what we have seen here. Already we discussed this. So you have condensate traveling at this 2 meters per second and steam 30 meters per second. Now, if steam drags this at 30 meters per second, then you have this shock waves, pressure waves that are created, which can damage many of the structures. Okay. So the trap is a very vital part of the steam system. The trap ensures that the heat is transferred to the product. The trap ensures that all the condensate is effectively removed and also ensures the non-condensables like air and other gases are vented out. And we have also seen the delicate nature of the assembly of the traps. So anytime it can malfunction, a small speck of rust or dust can make the trap leak, and leak can be terrible. So a typical trap, you will find in a typical industry, a process industry, a small scale textile industry, you will find at least about 25 to 30 traps. In a refinery, you will find 15,000 to 20,000 traps in refinery. So even if it, say, a trap is leaking 1 kg of steam per hour, say 15,000 traps means almost 15 tons per hour of leaks will be there. So a lot of care has to be taken in operation, selection, operation, maintenance of steam traps. So to avoid that rust and other particles affecting the trap operation, we have this kind of strainers in place. And as I said, different type of traps for different applications. And we want to know, because most of the cases the traps are fully closed. We don't know what is happening inside because there's heat exchanger here, and you have the steam going in, condensing, and then the condensate coming out, the trap. From the trap, mostly it is lifted directly to the boiler. So boiler it goes. So the trap, we don't know what is happening inside the trap, whether it's working or not. Suppose if it is an open case where the trap contents are emptied into a tank like this, then we know the steam is coming or condensate is coming. So in a closed system, we need to monitor the traps. Steam monitoring can be done many ways. So simplest is you measure the temperature here using infrared gun. You measure the temperature here, outlet of the trap, infrared gun. If the temperatures are the same, then trap is working all right. If the outlet temperature, if the temperature is same, if the temperatures both inlet and outlet are same, the trap is not working properly because it is allowing the steam to come out through the trap. So ideally, when steam condenses, only when condensate is coming, the condensate temperature will be lower compared to steam. This difference is used in this kind of infrared detection of the steam trap working. And also, the steam trap can fail by being open always. Whether steam or condensate is opening everything, then there is a loss. So there is a steam that is continuously carried away along with the condensate. The other failure is completely blocked, closed. Whether it is steam or condensate, it is not allowing. In such case also, there may not be a loss, but the product, the process cycle will get affected because it is not going to get heated. There is no continuous supply of steam because the trap is blocking. So failure, the open position or closed position, we need to identify. Some traps have this kind of gauge, visual gauge, from which you can identify whether it is working or not. So now if you see the liquid flowing, then the condensate is flowing from here. So it is working. And ultrasound is another method, like a stethoscope. This is like a stethoscope. Before and after the trap, you hear the noise. Before the trap, steam also will be there. So it makes some kind of noise. After the trap, only liquid will be there. It makes another kind of noise. So when only liquid is coming, you can identify the noise and see whether the trap is working or not. So this is again a very useful measure. Steam trap testing stethoscopes are there. There's an infrared we are talking about, a typical infrared gun. Before and after the trap, there should be a change in temperature, reduction in temperature. So now we have seen about the steam distribution system, what are the components and how steam transfers the heat. So how are we going to save the steam? The standard opportunities that are available are, as we said, monitoring the steam traps. Steam traps, if it leaks, it can be quite costly. So you're losing steam, and also the process cycle times you can upset. The quality of the product itself can deteriorate, or it can be different from what you expect. So steam trap is an important device. It has to be monitored, continuous monitoring of steam traps and taking corrective action. So many times when steam trap fails, there is always a bypass. This is something which you will find in practice. See, one of the problems in the industry is everything is a quick fix solution. So you have a steam going in, and then the trap is here. Okay. Now this is outside of the trap. Now what normally you will find, there is also a bypass with a valve. This is provided, this bypass system to the trap. When the trap fails, okay, you open the bypass. Or when you start the system, there will be heavy condensate load because everything is in cold condition. So heavy condensate load. So they open the bypass also to allow condensate to freely flow. Then they should close it. But normally this is always kept open because the trap, nobody wants to check the trap. It's a laborious process. So they keep this bypass open. That means continuously some steam will be going out through this. So monitoring of traps is very important. And leakages, steam leakages. It's a very simple thing, but it costs money on a continuous basis if you calculate. Suppose there is a plume length, there's a flange like this, and in the flange there is going to be a leak. So the leak will have a plume like this. This is the plume length. So the plume length is about, say, 400 mm, and the steam loss is somewhere around this. Okay, so you can estimate what is the steam loss. Providing dry steam for the process, we have seen why dry steam is essential. The wet steam reduces the heat content of steam. So that means you have to use more steam because the enthalpy of steam will be less, and also your process cycle time will be more. So always provide dry steam for the process. This is by controlling the boiler parameters, you can produce dry steam. Or if this happens normally when in a typical case, if you take a boiler is there. So from the boiler, there's a huge distance to a process. Say about more than 600 to 700 meters if it is going. So here it may be saturated at the boiler end. But gradually as it goes, at this point it becomes wet because of the condensation and loss to the environment. So what some of the industries do is they slightly give a superheat to the boiler, maybe 10 degrees or 20 degrees superheat. So by the time it reaches the end point, it becomes saturated. Okay. Or sometimes these are very special cases, they use steam separators, like a cyclonic action it creates. The water higher droplets being heavier, they drop down, and the dry steam goes out like this. Utilizing steam at the lowest acceptable pressure. So we have seen that why lowest? Because the enthalpy, the latent heat is maximum at the lower pressure. But at the same time, it has to be acceptable because the lower the steam pressure, the lower will be its temperature. So you have say 9 bar steam, saturation temperature is 173. 173 is going to heat exchanger, but on the other side you want to heat the oil to 190 degrees centigrade. Then that means this 9 bar steam is not sufficient. You may have to go in for 11 bar steam. So there is a limit to the reduction of steam pressure. You cannot always operate the lowest pressure, but lowest practicable pressure. And this is direct injection of steam, where you inject the steam through a sparge pipe called openings in the pipe. The steam goes and through this heats up the liquid. Cleaning of heat exchangers plays a major role. if you see the typical heat exchanger, there is this metal heating surface. So this is a metal heating surface. One side you have steam, the other side you have the product. Adjoining the metal section, there is a scale, the condensate film, an air film, and then steam temperature is 121 degrees centigrade. It has to cross through all these barriers, air, condensate, scale, and finally this side of, if it comes, you have scale, this is stagnant product film, and then through the product has to come out. So finally the heating up is done to 99 degrees centigrade. For 99 degrees, you have to necessarily maintain 121 degrees. But if you clean the heat exchangers, so the scale is not there, and condensate film by proper removal of condensate, air film, proper removal of air, and this scale also frequent cleaning. When you do this, then it is sufficient if you maintain say 110 degrees centigrade without all these barriers. You just need to maintain 110 degrees for getting the same 99. So accordingly, your temperature or the steam reduces, or pressure of the steam will reduce, your flue gas temperature will reduce. So you save on the fuel. This is air venting, an important comment, as we have seen how air venting can damage in terms of showing a pressure which is not exactly the steam pressure, and also acting as a barrier to the heat transfer. Condensate recovery, all the steam that is condensed has high temperature and also very good quality of water. Every 6-degree rise, 1% saving of fuel in the boiler. So you save on the money for financial reasons, and also the water. Water is a important commodity. You have to save water. So you return the condensate. Effluent. If hot condensate goes to the effluent treatment plant, then the bacteria will die and the ETP operations will get affected. So you need to better to recover than cool it, then maximizing the boiler output. If you send hot water to the boiler, you will get more steam. So 5 tons per hour, you may get 5.5 tons per hour when you recover the condensate. And boiler feed water quality also improves, or the cost of treating the water reduces. And the condensate is pumped back to the boiler because it's a hot condensate, 90-95 degrees centigrade will be the condensate temperature. A typical centrifugal pump may find it difficult to pump it. So we use what is known as a steam powered pump, very commonly used. Either we use a submersible pump or a steam powered pump, which the condensate is collected, and after a while the steam is injected into the cylinder, and the cylinder pumps the condensate to the boiler. Insulation, as we have seen, is important. So insulate all steam pipelines and hot process equipment also we need to insulate. The flash steam is a steam, as we have seen. Suppose you have a heat exchanger, 9 bar steam is coming. So inlet is 9 bar steam, and outlet is 9 bar condensate. It has given the latent heat to the product. The 9 bar condensate will have a saturation temperature of 170 degrees centigrade. Now this, when you release it to the atmosphere, it will flash into steam, vapors. So what we do is we take this condensate in a flash vessel. So it is a flash vessel, and so you have a low pressure line, let us say 2 bar. So what we can do is we flash it to a low pressure, that is 2 bar, and it becomes 2 bar steam. 2 bar steam can be used for some of the applications in the plant. This flash.
Sir, your voice not audible, sir.
எனக்கு அப்படிதான் இருக்கு. I'm not able to hear anything. Kripakaran sir, am I audible? Nagesh sir, you are not audible, professor.
Hello, sir. I'm Sagar here.
Yes, sir, please.
Sir, audible, sir. Your voice.
No, I am audible. How about him,
Yes,
sir?
sir.
Nagesh sir.
Okay, sir.
Joining again. Okay. Now, can I address it now or you want me to ask him like? I don't know if we can go to the program. 4:30 we can. Just ask him if he can handle or I'll handle the session. Good evening to all. I think there is some issue with the speaker. So I take this as an opportunity whereby I'll be able to handle the topic what that was half covered in the early morning session, the first session. We were seeing about energy scenario of India and the importance of energy audit, all those things and all. Let me share my screen so it becomes helpful. One minute, please. Yeah, we were onto this interesting energy facts, like, and we have seen the facts about India, and we were onto this one, the environmental impacts of energy usage. There are two broad impacts. One is called as greenhouse effect, other one is called as ozone layer depletion. We will see about the greenhouse effect first, and then accordingly we'll have the ozone layer depletion. See, one basic thing what we people have to understand is that invariably at any time, if I get into the car, the interior of the car
Okay.
would be warmer than the exterior. Nagesh sir, you come sir.
Ah, yes, sir. Yes, sir.
Yeah.
Yeah.
Yeah. Okay,
Shall
sir.
I-
Then I'll do one thing, sir. I'll go off so that accordingly you
Yeah.
can
Thank you.
have your
Thank you very
session.
much, sir.
Continue,
Yeah.
sir. Start, sir, please.
Yeah, yeah, please. My screen is visible?
No browser.
Sorry?
No,
No,
sir.
sir.
No.
No, sir.
No. Okay, okay. Just hold on.
Visible, sir.
Yeah, okay.
Yes, sir.
Right. So we were looking at the the flash steam. So this is called a flash vessel. So in a process equipment, let us say we have some steam coming from different condensate coming from different process equipment. It comes here, and low pressure condensate, when it sees a high pressure condensate, when it sees a low pressure, it flashes into low pressure steam. So here what you get is a low pressure steam at say 2 bar. Here it may be coming at 9 bar condensate. In the flash vessel, it flashes into lower pressure. So you get 2 bar steam here. So 2 bar steam can be used for some other applications. This is a flash steam concept. And in many of the industries, you'll find that pipes unnecessarily running here and there, where the department itself will not be using steam anymore. So many changes have taken place, but still pipelines are running here and there. So cut down all this unnecessary piping. That itself can give you a lot of savings. Then reducing the work to be done by steam. If you see, it's like our washing machine. When you wash clothes, what happens? Finally, we completely squeeze the moisture, squeeze the cloth to get rid of as much moisture as possible, like a spin dryer in a washing machine. Then you put it in the clothes line, quickly the drying takes place. That means you are reducing the work to be done by the sun. Similarly, in industrial processes, there are these equipments like, which can minimize the, like in a dryer case, minimize the work to be done by a steam. So here we have what are known as hydro extractors, in which we completely remove as much as possible the moisture, and so the amount of steam required will be less if you have lower moisture content. So in this case, 48% moisture means 62 kg of steam is sufficient, whereas here 52% moisture means 67 kg of steam is required. So there are a variety of ways in which we can reduce steam. Probably we can look at some of the case studies in the next 15 minutes. We'll look at some simple case studies so that you can understand. See, one of the simplest thing here, this is a hot water boiler. Instead of steam, they're using a pressurized hot water. This is something which is there in the industry. So instead of making steam and having a boiler, if you want, say, dryer, for example, this is a mosquito coil manufacturing plant. The mosquito coils are stamped, the shapes are made, and then they are put in a drying conveyor. That's all, simple process. So this dryer has to remove the moisture. So the dryer temperature is made at 80 degrees. For 80 degrees, we don't need steam. So what some of the industries do is to have a pressurized hot water generator. So if you have a pressurized hot water system, you can raise the temperature to 120 degrees or 130 degrees without making it into steam. So a hot water temperature itself will be 120 degrees in pressurized condition. This pressurized hot water is going into the dryer. Fan is blown on the heat exchangers carrying the hot water. Hot air goes in, 80 degrees maintained, dried mosquito coils come out. This is the system. So in this system, uh, see, in the case of, okay, this is the briquettes that are being used as a fuel. Already the industry is very smart. They go in for the least cost fuel. So this is a sawdust briquette widely available in that area. And here the hot water generator is a single pass design. Single pass means the combustion chamber, it goes into the heating vessel and then goes out. Single pass. Double pass means goes here, comes here, like this. Triple pass means goes here, flue gases come like this, take again a turn, again go out in the chimney like this. So this design is single pass, exhaust temperature is 270. Now here we are putting a heat exchanger to recover the heat. Since the fuel is cheap, they assume that you can keep a higher temperature in the exhaust. But by recovering this heat, by providing one more heat exchanger for preheating the hot water will be in circulation. From the hot water generator, it gets heated up to 130, 150 degrees. It goes to the dryer, comes back at about 90, 95 degrees. So this is a circulation that is taking place. Before it reaches generator, you have one more heat exchanger in the exhaust. So like what we have here. The hot water generator. So briquettes are fired. So the flue gases go through like this. Then there is a scrubber. And then there's a multi-clone for the dust. And finally, okay, here we are putting up a heat exchanger. Then you have an ID fan. So when you do this, after doing this, the temperatures, the amount of briquettes that they needed to fire was reduced by nearly 10%. So it saved them about 16 points, 272 tons of briquettes per year they could save. So the investment is 10 lakhs and paid back in 8 months. This is one simple case. See, when you're looking at steam savings or heat savings, there is a lot of integration that is required in the industry. There's a dryer part. You can see the mosquito coils getting into the dryer. So now that hot air is required at 80 degrees in the dryer, this dryer. Adjacent to the dryer room, we have these compressors, air compressors. There are 3 air compressors, screw compressors. And as you know, the efficiency of a compressed air system is only 10%. 80% of the energy that you put into the motor, it goes out as heat in these ducts, ventilation ducts. Now, this is hot air at 80 degrees going out into the atmosphere from all these 3 compressors. One is 45 kilowatt, another is 45 kilowatt, this is 90 kilowatt. So a huge amount of heat is available in these ducts thrown to the atmosphere. All we need to do is, if there is an opening here, window. Now, if you open this window, you provide a duct and connect this duct into this dryer. So you will get free hot air at 80 degrees, and that will again reduce the hot water or the steam consumption, and the briquettes consumption also reduces. So this is the firing part for the briquettes. Recovery of heat from air compressors, ventilation. So area of the ventilation duct is this much. So we have found out this is the mass flow rate of air. The temperature of air, 70 degrees. So depending on if it is insulated, you may even get 80 to 85 degrees centigrade. The ducts are not insulated. So the heat recover, what is the heat available in air is this much. So about 10 kg per hour. This comes to about 4.8 lakhs. Conservatively, if you see, 4.8 lakhs is savings by just diverting that hot air to the dryer. And if you want to save steam, the first thing that we look for is to make a steam balance. In a typical plant, this is a boiler. So for the boiler, you have a distribution header. So make a flow chart like this, and wherever possible, measure. As we said, open out the trap, collect the condensate in a barrel or a bucket, and see what is the time taken. You can find out what is the condensate flow. That will be the steam flow as well. So this is a flow chart, and where you cannot measure, you can calculate indirectly by uh, MCP delta T method. Whatever the heat transferred, and from that you can find out what is the steam consumption, or you can estimate, or in the worst case also guesstimate, so that you get a fairly decent steam balance. So you should know where to focus your attention, where steam is consumed to the maximum, where you should focus. And with respect to the production, it's always good to have what is known as specific steam consumption per ton of product. What is going to be against the production? This is a production. What is going to be my specific steam consumption per ton of product? What is the specific steam consumption? So it has got a direct bearing on the production levels. In this month, the production was very low. Lower production automatically meant higher steam consumption per ton of product. Specific steam consumption is higher because of lower production. Higher production means automatically the specific steam consumption goes. So one of the best ways of saving steam is to produce maximum without any interruption. If you can produce maximum without downtime, without interruption, if you can produce the maximum capacity, then you are optimally utilizing the steam. That is the first principle. And yeah, the second thing is you can look at the blowdown from the boiler, whether is there a possibility of recovery of blowdown steam, blowdown, whatever blowdown is given, we can flash it, and then many of the plants take that flash steam to the deaerator part, where the feed water is heated about 105 degrees centigrade and above to eliminate dissolved oxygen. And the next step will be to make a process flow chart, find out what is happening in the process, what are the various steps in the process, where the steam is used. So first understand the process, then understand in detail wherever steam is used in the process steps. You understand in details, and along with data, you try to make some calculations, preliminary calculations at least, and you will get a fairly good idea as to what is happening. Now, after doing that, we find that there is a huge potential here. So what we are doing is we are going to, this is the system what they had. There is a solvent, impure butanol. It is coming at 15 meters per hour and 30 degrees centigrade. And this has to be heated. So they are heating it to, and this is impure, has to be made into pure butanol. For that, there is a two-step process of heating and cooling. Steam is used to raise it to 124 degrees centigrade, and it cannot be stored at hot temperatures, so immediately it is cooled by cooling water, cooling tower, which has got a 37 kilowatt pump. 124, again it is cooled 40 degrees. This is the system. Now, what we are going to do is there is a heating and cooling. Now we are heating it with steam and cooling it with cooling water. Instead, can we use this pure butanol? Here, this pure butanol, what we are going to do is use as a cooling medium. So here you have impure butanol coming, and pure butanol at 124 degrees. So this 124 degrees is to be cooled to 40 degrees. Now what we're going to do is this 124, we are going to take this line here and put a heat exchanger and preheat this impure butanol which is coming. So what we have taken is, we have taken this line here from here, 124 degrees. 124 degrees, we have put another preheater here. Before the evaporator column, we have put a preheater. So pure butanol goes here, 124, and it gets cooled to 40 degrees. So this cooler is not at all required. So incoming impure is 30, it gets to 80, and little more steam you add 75 kg per hour, you get 124. So here you save on the steam 130 kg, it has reduced to 75 kg. Cooling water pump completely eliminated. So steam savings alone is about 3.6 lakhs per annum. So this is called the process integration. So when you study the process in detail, there is a lot of scope for integration. And this is a very simple process, the tube molding machine. So here the curing is done for the tubes. This is a mold. So if you go around this area, it was too hot, very difficult to remain in that place. And if you see the source of heat, it is basically from this molds. It's about 160, 170 degrees centigrade. These are radiating. So now attack the source of the problem. So how we can prevent it? Simplest thing is to provide a insulation around this mold. So the radiation from molds can be prevented and energy can be saved. So after insulation, the temperature was only 40 degrees. So they were able to save about 5% on the fuel. Textile plant, you see, this is a typical case. Like this, there are many opportunities. So when you're looking at steam, first you have to look at the process which is using the steam. The textile fabric dryer. Cylinder length is almost about 3 meters. Cloth width is only 1 meter. Now, steam is going into the cylinders, heating up the cylinder, and this hot cylinder will dry up this cloth. Now, you can see this radiation from this sides, and from the cylinder sides, this is consistent. So, now what we need to ask is whether we can feed two sets of fabric, one set of fabric here, one set of fabric here. So, you can increase the production as well as minimize the heat loss from this cylinder. And simultaneously, the sides of the cylinder can be insulated, the end of the cylinders. So this was done actually, the end of the cylinders. This depends on the production scheduling and other constraints will be there. But here is an opportunity where you can insulate. And it required, there is no off-the-shelf market availability for such insulation. We have to design it accordingly. So, and heat recovery, like hot water generation from these kind of waste sources. Singeing is one process in textile industry where the small fibers are burnt using LPG, and this is connected in a hood and then taken out. So we can generate hot water of 70 degrees, which can minimize the steam consumption. This is a case of a power plant where, as we have seen, see the steam basics, we have seen the T1 minus T2 by T1, increasing the inlet temperature to the turbine. So the inlet, in this specific case, the inlet temperature to the turbine is maintained at 500 degrees centigrade, though the upper limit for this turbine is 516. So we made a trial. What will be the situation when you increase the temperature from 500 to 505, 510 like that? So the existing temperature was 500, and finally we increased it to 500. Up to 510 we were able to increase. So there was an increase, additional power output from the steam turbine. Just from 500 to 506, 6-degree rise in inlet temperature turbine, you get additional 180 megawatts. So kilowatt, sorry, this is not megawatt, this is kilowatt. 180 kilowatt additional you get. So we have seen pressure reducing turbine. Now this we can see this. Yeah, this is where we said no, two fabrics in one stroke. Instead of using one fabric in the entire section, use two sets of fabric. Wait, that means the production scheduling is involved. So you schedule in such a way that two fabrics are available, then you start the machine. Now this is a case where you can effectively, instead of using pressure reducing valves, what we are going to do is, here there's a tire factory having a 20 bar steam and 20 tons per hour. So initially what they had was a pressure reducing station, a PRV, which will reduce from 20 bar to 10 bar, 10 bar further to 3 bar, 5 bar, like that. And this is a process. So what we have done is from 20 bar to 10 bar, instead of a pressure reducing valve, we have put a steam turbine. Now the steam turbine is generating about 212 kilowatt of power. So earlier it was wasted through. See, pressure reduction means it's an isenthalpic process. We are killing the pressure through the pressure reduction. Instead of killing it through the valve, we are putting a turbine and generating the power. So you get 20 bar at inlet and 10 bar at outlet, which were the conditions earlier when the pressure reducing valve was used. So like this, there are many innovative solutions for steam conservation. As we said, the efficiency of utilization is only 47%. So there are a lot of opportunities if you focus on the process and also on the utilization side. Okay, so I'm stopping with this. Any questions you have?
Participants, if you have any questions related to steam utilization, you can discuss now. Okay, sir. I hope they don't have any doubts.
Yeah.
Thank you very much, sir, for spending your valuable time. And
Yeah.
I'm very sure that the session was very fruitful to all the participants, those who have attended this session. Thank you very much, sir.
Thank you, all of you, for the patient listening. Thank you very much.
Thank you, sir.
Thank you.
Participants, please submit your feedback and attendance form. I have mailed to all the registered candidates, as well as the link is shared in the WhatsApp group. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.